rest and motion are relative terms. If you are inside a train which is moving with some speed, then other passengers in your compartment may not be moving with respect to you. But somebody watching the train from outside would say that the train is moving, and so all passengers inside the train are also moving. So it's a question of who is observing. Observer is the key. So we often choose some observer and we try to analyze if something is changing position with respect to that observer or not. If something is changing position with respect to the observer, then it is in motion with respect to the observer. But if it does not change its position with respect to the observer, then it is at rest with respect to the observer. There are some physical quantities that we need to talk about. Almost all of which you are already familiar with. Distance and displacement. Consider some observer. You can choose that observer as the origin in X, Y, Z. With respect to that origin, some position is changing. Let's say in this manner. Then this whole thing, if you measure the length of this whole thing, maybe you can place a thread here and then straighten that thread and use some scale and measure. Total length of that journey, that is called the distance. Distance is a scalar quantity. It has no direction. But if you just focus upon the final and the initial points, you join the 2 points by a straight line, mark an arrow pointing towards final position, then that thing is displacement vector. If you measure its length, it will tell you the magnitude of displacement vector. Arrow is already telling you the direction of displacement vector. So interestingly, if you have any closed journey, like going to the school and coming back, that's a closed journey, or going to a shop and coming back, it doesn't matter how you go there, as long as it's a closed journey, you are back at the same place. Your displacement is always zero. You go there and you come back. If your final position meets your initial position, then there is no displacement. But the distance can be substantial. It all depends on the situation. Displacement is vector, distance is scalar. When we talk about speed and velocity, we see how quickly these things are changing, distance and displacement. But before that, one more point I would like to say. Displacement can be zero, but distance is normally not zero unless it's a rest case. In fact, distance will never be zero unless it is a rest type of situation. If the particle is at rest, there can be no distance covered. But if particle is not at rest, there is going to be some distance covered, but displacement can still be zero. If final position is same as the initial position, even though in between these two there are several position changes, displacement can still be zero if final position is same as the initial position, even though there are several different positions in the journey. That never happens with distance. If there are several positions in the journey, distance can never be zero. So, it is not always correct to say that magnitude of displacement vector will be distance. Magnitude of displacement vector can be distance, but not always. And when is it going to be distance? Magnitude of displacement vector, when it's a straight line motion in one direction. If somebody travels from A to B, absolutely straight, then magnitude of displacement vector is the length AB, distance is the length AB, they are the same. But if there's a turning involved, then they won't be the same. So only in one condition you will find that magnitude of displacement is always equal to distance. But otherwise, the general rule is that magnitude of displacement is less than distance, or to make it absolutely general, magnitude of displacement is less than or equal to distance. Now, I was saying earlier about change in these physical quantities, distance and displacement. So we have physical quantities called speed, velocity. They are to do with this, how quickly distance, displacement are changing with respect to time. Now, in a very special case, it may happen that in same time, same distance is covered. Imagine every second 1 meter is covered, every second. Initial 1 second of the journey, next 1 second, next 1 second, next 1 second. In equal time, if you cover same distance and you continue to do so, that means you have got constant speed. Speed is, in that case, distance upon time. And that is the simplest definition of speed. Speed is equal to distance upon time. But it is not always a very correct definition of speed. Speed is equal to distance upon time is fine as long as it's constant speed. But if it is not a constant speed, which is what happens normally in practical situations, then if you say speed is distance upon time, then it's average speed you are talking about. If it is changing all the time, then how can you say one single speed will be equal to distance upon time? It is changing all the time. So speed is equal to distance upon time is fine if speed is fixed, same at every instant of the journey. But if it is changing, then one should say average speed is equal to distance upon time. Now comes the key question. If average speed is distance upon time, then what is speed? What is the meaning of speed? Normally the meaning of speed is the instantaneous speed. If a car is traveling, what its speedometer is showing, that is called the speed. And that speedometer can show different readings at different instants of time. Instantaneous speed is what speed is, generally speaking. So when speed is changing every now and then, and one can talk about average speed, fine, but how does one talk about instantaneous speed? That's where calculus is so important. So the speed is ds by dt. ds by dt. Basically what we are doing is this. Suppose we want to know speed here, the true speed, then we will take very small distance, call it delta s. Suppose that distance is covered in delta t time. Then the average speed in this interval is delta s by delta t. Now make delta t very, very, very small. And that will become the true speed at that instant. So likewise, you can talk about instantaneous speed at various points. The smaller you make delta t, the better result you will get for that particular point. So speed is ds by dt. You know the meaning of differentiation graphically. Graphically, it is the slope of tangent at a particular point. Slope of tangent at a particular point. So suppose I have got S versus T graph. Distance time graph. Which will depend on the motion. How is the motion? It will depend on that. Suppose I take some arbitrary shape. From this graph, I want to know what is the speed at so and so time. So I would need to draw a tangent at that point. This is the tangent at that point. I would need to find this angle theta. Then tan theta is same as ds by dt at that point. If I don't want to do all that, if I don't want to measure theta, I don't want to draw that thing, then I need to know the mathematical relationship between s and t. Not the graph, but the mathematical relationship. Say s is equal to something times t square plus something times t minus something times t cube or whatever. Some expression I need to have for s. S equal to something in t. That I need to have. And if that is what I have, then it is so easy to differentiate. You know various formulae for differentiation, various theorems for differentiation. So you can find ds by dt. And then you will say you want ds by dt at t equal to maybe 5th second. So after you find ds by dt, You put t equal to whatever, 5 seconds, and that will be your same answer. Same answer. So to get the same answer, you have two approaches. Either you draw the graph, or if you have the graph, draw the tangent, find theta, then find tan of theta using trigonometric table or calculator. Or if you have mathematical expression, s equal to something something in t, then differentiate, and after differentiating, put t equal to what? You should never put first t and then differentiate. Right, so that's the way to find instantaneous speed at a particular instant of the journey. Then, if we say that v is ds by dt, then it also means that s will be, let me write one more step, s would be integral v dt from initial time to final time. So if I have got VT graph, speed time graph, it depends on case to case basis how it would look like. And I'm interested in these two time intervals, these two time interval is t2 minus t1. Then area under the curve, this area, that is what is S. That is what is S. Geometrically, I can do it. How do you find area of a shape like that geometrically? You will have to make some approximation. If you want to find the area of some arbitrary shape, you will divide it into several strips. Smaller strips, if you can take, better it is. Because you are going to call these strips as rectangles. And your approximation to call these rectangles will be better if they are really thin. Otherwise, this curve part will make your approximation bad. Rectangle is not supposed to have curved part. So you divide this into as many strips as you can. Treat each strip as a rectangle and add after that. So that's an approximate way to do it. But if you have a mathematical expression b equal to something times t minus something times t square, whatever, then all you have to do is to integrate. You know the formulae and theorems of integration. So it will be very easy to integrate. And after you integrate, put the limits t1 and t2. We are basically doing definite integration. Put the limits and you are done. So if you have got ST graph, you can find V. Yeah, if you have got ST relationship, you can find V. If you have got VT graph, you can find S, or if you have VT relationship, you can find S. Speed is roughly speaking distance upon time, or more correctly speaking ds by dt. So dimensionally speaking, it will be LT minus 1. Any questions? Let me know. S equal to 2.5 t square in this expression, take the unit to be SI unit. Since we already have mathematical expression, we can directly differentiate to find instantaneous speed. Never put t equal to 5 first and then differentiate. You will get nothing but 0. 0 as the answer. First differentiate and then put t equal to 5. Constant comes out of derivative. What is the derivative of t square?
So 2t.
Correct. So you got 5t. Now put t equal to 5. Mathematically we can write it like this. (25 meters per second). Any questions for instantaneous speed part, or we go to average speed part? Would you like to try the average speed part first? Try this, then I will discuss it. Okay, now I'm doing it. Let me copy this board. Now, average speed is total distance covered divided by total time elapsed. Total time elapsed is clearly 5 seconds. The question is how much distance that is covered. When t was 0, S was, put t equal to 0 here, you will find S was 0. Maybe the particle was at the origin, and when t is 5, then S is how much? 2.5 into 5 square, which is how much? 25 into 2.5. Now we have to divide by t, so let's keep it like that. So how much is S final minus S initial? Actually it is delta S. It is often convenient to think of position. Think of S as position. Think of S as position. In fact, I would like this word here. The position of a particle in time t is given by this position of the particle. Position of a particle moving in straight line is given by this. So delta S will be S2 minus S1. This is S2, this is S1. Delta T is final T, T2 minus T1, which is 5 minus 0. $12.5. Any questions? Let me know. It's a VT graph. In VT graph, the area under the curve tells you the distance traveled. Question has not given us the mathematical expression, but has given us the graph. So we would go for the area method. Area under the curve is this.
Sir, 3 meters, 9 meters.
9 meters. 9 meters is right. In this case, it's a triangle, so it's very easy. If you have any questions, then let me know. Half into base into height, basically. Actually, it's a right angle triangle. Use the definition only. Don't make any assumption. Just use the definition. Detailed working is optional. That's your assignment question. We stop now.